Okay, so the next unit we're going to be doing is Chapter 6, and this unit is going to be all about integration. Okay, that's the actual name for in the textbook. So you can look in the textbook, right, to go along with this. You can see that today I'll be talking about section 6.1 right here. Okay, and so please, if you haven't already, print this out, the sheet out, or just kind of do it along with me in the notes. If your printer's not working, that's fine, right? But don't just watch me do it. You need to make sure you're doing these to help you to do the homework. Okay. So we have a student in Mr. Noorzai's class has built a self-propelled miniature car that runs on renewable energy. The student is testing out the car by checking its velocity at certain times as shown in the graphs below. The independent variable is time and the dependent variable is its velocity. Estimate the distance traveled by the car over 0 to 10 using the given data points. And we're going to say that these are seconds here, right? And we'll say that, because I don't think it gives us labels there, and we'll say that these are, this is feet. Okay, or I should say feet per second, because these are velocities, right? Right. So, so it's not like the car just started from 0. It's just saying, you know, it's running, and then these are some different velocities. So we can see that the velocity at 0 seconds is 4, velocity at 1 second is 4, velocity at 2 seconds is 4, velocity at 3 seconds is 4, velocity at 5 seconds is 4, velocity at 6 seconds. I mean, every single time period, this could be 4. This could be done in the form of a graph, right? If this was or a table, right? It might give you a table where it just says here's a time, here's a velocity. So, but this one is actually graphed out for you, right? So if this was in table form. Not that you need to write this in table form, but I'm just saying, right, this is in graph form. If it was in table form, you'd have something like a time and a velocity, and then you would have all your information. So 0 was at 4, and 1 was at 4, and 2 was at 4, and 3 was at 4, and 5 was at 4, and 6 was at 4, and 7 was at 4, and then 10 was at 4. Okay, so this is how it would look. So you know, some problems will give you graph form, some will give you table form, and it's really the same thing. Just it's two different ways to represent the same thing. Okay, so if we think about this, I think it's pretty safe to say for this that the velocity is always 4. It's 4 in all cases. I hope you would agree there. Like if we just keep taking all these random measurements, right? It's 4. Now there's some possibilities that it goes up or down from there, and just happens to be coincidentally always at 4. But we can't go by what might have happened. We have to go by the information we have here. So this is going to be an estimate that we have here, right? So we can guess, we can estimate that the velocity is always going to be 4. So if we think about that, if your velocity is 4, and let's see, right, the velocity equals 4, and the amount of time it traveled at that velocity. Well, if we think about that, if you travel 10 seconds at a velocity of 4, right, then you would say, oh, well, distance equals rate times time, right? Rate times time. So we could just use that, and we get the 4 times 10. If we look at what we have here in our actual shape, right, we have this coming up right here, right? We can see that this is also a rectangle that has a height of 4 and a width of 10. And the area of that rectangle is 10. So velocity is really just, distance is really just finding the area of your rectangle as you work through those. Okay. Okay, so that was that example, and this one is a pretty basic, straightforward, because the velocity was always the same. So what do we do if the velocity is changing, like we have in this case right here, right? In this case we have the velocity changing. So there's for ourselves. So in this case, if we'd made the table, right, my table form for this would be something like this, right? 0 is at 1, 1 is at 2, 2 is at 3, 3 is at 4, my next rating is 5 is at 6, and then a time of 6, the velocity is 7, and a time of 7, my velocity is 8, and then 10, at the time of 10, the velocity is 11. So we can see in this case now it looks like it's the velocity is going up. It almost looks like it's linear, right, for myself. So I could definitely say to myself, hey, look, I can put a straight line through all of those. Right? It looks like it's going up at a nice, right? So if I'm going to think about this, right, how am I going to find the total distance traveled? Remember, that's the question here that we're doing. Estimate the distance traveled by the car. And again, it's an estimate because we don't have every single velocity. Okay. So, as I just said in the previous one, right, the distance is just basically your area under the graph that we have here, your area under the curve. Right? In this case, it was a rectangle. Now, if we can't do rectangles here because if we look at the top here, it's kind of slanted for myself. So what could I do instead? Well, I could think of it as a giant shape like this right here. Okay? If we think back and said, hey, this was a rectangle here in shape, and it was just the area under the curve, I can do the area under this curve, and this will tell me how far I traveled. So, right, instead of doing lots of little rectangles for myself. So for this one, I could just say, okay, what's the area of this shape? And that shape's a trapezoid, and to find the area of a trapezoid, we do 1/2 the base 1 and plus base 2, and base 1 is 1 here, and this is 11. Right. And the height of it is 10. Okay, and so if we look at that, that's 12, right? Half of 12 is 6. That's 60. Okay, I should put feet on this, and I should put feet on this. Okay, so the area under this curve is 60. So if we were going to think about how far this traveled, if we assume that this is linear for ourselves, we'd have 60 feet that it traveled in those in those 10 seconds for ourselves. Okay, all right. So we've just found the area under that curve and found that distance there. Okay. Now, if we're looking at something that's more random here, now this one, it looks like there might be some problems with the car, right? And if we're doing this, it's jumping all over the place, and I can't just it's not just linear. You can see it's every which way, right? So we have lots of different strategies we could use to try to estimate this. Okay, so one way we could do it is we could try to make rectangles, because rectangles are the easiest way. So if I think about this, I'm going to start, right? Step 1 when I'm doing this is to take a straight edge and to just draw down to draw the verticals in for myself. Okay, and this will help me to create my rectangles for myself. Okay, so and these are all the intervals for myself, and these are the only actual velocities that I know. So what I could do for this first interval is I could make the assumption, right, that the velocity was 0 for throughout the entire thing. So here's my rectangle, right? So for interval 1, I could assume that it has a height of 0 and a base of 1. So basically, it traveled 0 units in that first interval. Okay. Then, our next reading is a velocity of 3, 1, 3. Okay, let's make the assumption, right? And remember, because we don't have every single data point, any assumption is just as good as another, right? That the velocity is 3 throughout this entire interval. Okay, so if the velocity is 3, it's just going to stay constant there, and we create ourselves another rectangle. If we look at that rectangle, we'll call that interval 2. Oh, I'm sorry, I should call it subinterval, because the whole thing is the interval. 0 to 10 is the interval. So this is my subinterval, an interval within an interval. Right, in the subinterval, it has a base of 1 and a height of 3. So this rectangle has an area of 3. And if we think about it, if you were to travel at 3 feet per second for 1 second, we've traveled 3 feet. So in the first subinterval, we'll travel 0 feet. In this one, we travel 3 feet just by finding the area of that rectangle. Okay. If we do the next subinterval, right? Let's see, this subinterval number 3, right? I'm going to stick with what I've been doing so far and using this left endpoint, right? And assuming that stays constant throughout the entire interval. Okay, so I'm just going to make that assumption. Okay, and so that has a, if we look at how long the subinterval is, it is a length of 1 again. There's 1 unit there. How tall is it? It's 6. So it's a length of 1 and a height of 6. So the area of that rectangle is 6. If we think about this, if you were to travel at 6 feet per second for 1 second, you would travel 6 total feet. Okay? For the next subinterval, right, let's assume that that this left endpoint, we're going to remain at that velocity throughout the entire thing, right? So that subinterval has a length of 2 units. It goes from 3 to 5, so it's going to be 2 units, and it has a velocity of 5 feet per second. So if you travel 5 feet per second for 2 seconds, that's going to be 10 feet you've traveled. And that's, again, the area of this rectangle. Okay? Right? 2 seconds at 5 feet per second, 10 feet. And that's an estimate. For the next subinterval, you can see that it has a length of 1. Right? This right here is a length of 1. Because it goes from 5 to 6. And if we assume that we maintain this left velocity throughout the entire interval, right, then we'll see that we've traveled 3 feet. Okay. This is a length of 1, right? If we assume that we maintain this left endpoint's velocity of 8, that means we've traveled 8 feet. Okay? I'm putting these in both spots so you can kind of see where the numbers come from, see how they relate to each other. Okay? You should be doing this along with me, right, on your notes, ideally from the printed notes. Right? This subinterval has a length of 3. If we assume that we maintain this velocity throughout the entire thing, which is 9, you say you're traveling 9 feet per second for 3 seconds, you get 27 feet. Okay. If you add all those together for ourselves, if we add up all those distances, 3 plus 6 is 9, 19, 22, 30. We have an estimate that we've traveled 57 feet. That's the estimated distance traveled over our interval. And about 57. I'll put the about symbol because we don't know. Now some people say, well, you didn't use this at all. You're right, I didn't use that at all. Because this one, I always use the left endpoint, right? The left endpoint's value, okay? And so that is called the left endpoint rectangular approximation. Okay? And we're going to shorten that by calling that left rectangular approximation. Oh, I forgot that method. We're going to call it LRAM. So LRAM is just saying, hey, this is varying all over the place. Let's use the left endpoint and figure out how far it travels if we use that left endpoint.